Hello everyone, this is Bandgar working as an assistant professor at Department of Physics, KTHM College, North. Today we have to going to discuss M.Sc second year semester 3 paper 3 experimental technique in physics first. Today we have to going to discuss the concept of vacuum physics, and today we have to going to talk the subtopic of vacuum and their concepts. So starting with what is the vacuum and what is the concept of vacuum. So vacuum, it is nothing but a generally defined as a volume of phase that is essentially empty of matter, such that its gaseous pressure is much less than atmospheric pressure. In real practice, no volume of phase can ever be perfectly empty. A quality of vacuum refers how closely it approaches a perfect vacuum. A perfect vacuum is simply called vacuum or fluids, and use the term partial vacuum to refer to real. The residual gas pressure in space of interest is primarily indicator of quality and is most commonly measured in units called torr. Lower pressure indicates higher quality vacuum, but practically impossible to achieve perfect. So vacuum, it is nothing but a free space. There is no volume of space, but practically we cannot get the vacuum. So when we get the lower pressure, so indicate that there is the high quality. Now second concept is what is the range of vacuum. So vacuum by range, vacuum has the 5 subtypes. First is the low or rough vacuum, second is the medium vacuum, next one is the high vacuum, next one is the ultra high vacuum, and last one is the extreme high vacuum, that is the denoted by XHV, ultra high vacuum, UHV, and high vacuum HV. So what is the range of that types? So first one is the low and rough vacuum, that is the atmospheric pressure to 1 millibar. So that is the range of low vacuum. Second one is the medium vacuum, that is the 1 to 10 raised to minus 3 millibar. Now next one type is the high vacuum, that is the 10 raised to minus 3 to 10 raised to minus 8 millibar. That is the range of high vacuum. Now next range of vacuum is the ultra high vacuum, that is the UHV. That is the range of 10 raised to minus 8 to 10 raised to minus 12. And last one, the extreme high vacuum, that is the XHV. That is the range of less than 10 raised to minus 12. So that is the range from 1 millibar to the 10 raised to minus 12 millibar. That is the range of vacuum from low to extreme high, XHV. Now, what is the importance, what is the need of vacuum? So, the measurement of pressure and vacuum in all industrial processes are most important. To avoid many hazards, it is essential to measure and control pressure on liquid or gases. It is quantitative determination of flow rates, mass flow rates, gases, or liquids. Pressure and vacuum play very important role in process control, as well as certain products decompose or polymerize, and some components can be separated by distillation at lower temperature when operating under. So vacuum and pressure, these two concepts are very important in a process control industries, and it is the easily measure and control liquid, gas, and both, and it is the very important to the generates the any new thing in a vacuum. So there is the no loss, no any hazards, or you get the proper without any distraction, without any error, you will get the proper output. It is the very important in a process controller in many industries. Now next one is the application of vacuum. So vacuum has the many applications. So starting with first, incandescent light learn to protect the filament from a chemical degradation. Now second one is the chemical interface produced bacteria. It is also useful for electron beam painting, gold painting, vacuum packing. Now next one, ultra high vacuum is used to in the study of atomatically clean substrate, choline, very good preservers, atomic scale clean surfaces for a reasonably long, on the order of minutes to day. High to ultra high vacuum removes the abstraction of air, allowing particle beams to deposit or move material without contamination. So these the principle behind the chemical vapor deposition, that is the CVD, physical vapor deposition, PVD, and dry etching, which are very essential to the fabrication of semiconductor and optical coatings and surfaces. So vacuum is very important, play a role in a material science which generates the very nanoscale, nanoscale films, nanofilms. Now, another application of vacuum is the reduction of the convection provides the thermal insulation of thermobottles. Vacuum, deep vacuum lowers the boiling point of liquids, promotes low temperature outgassing, which is used in freeze drying, adhesive preparation, distillation, metrology, and process. The electrical property of vacuum make electron microscope vacuum tubes possible, include cathode ray tubes. But interrupters are used in electrical switchgear. Vacuum arc process are industrially important for production of certain grades of steel or high purity materials. The elimination of air frictions is useful for lighting, energy storage, and ultra sensing. So these are the various applications, various fields use a vacuum for their application. Now, next concept is the kinetic theory of gas. So, kinetic theory of gas relate to the microscopic property of the gas, like the temperature, pressure, volume, to the scopic property of the gas, like speed, momentum, position. In this model, atom and molecules are continually in random motion, constantly colliding one another, and the walls of the container with which the gas is enclosed. It is the motion that results in physical properties such as heat and pressure. The gases are made up of a large number of molecules. They are flying in a random direction with a certain speed. By knowing their speed or position, one can figure out the macroscopic properties. In other words, by knowing the value of velocity or internal energy of gas molecules, one should be able to figure out the temperature or pressure. Now, next concept is the assumption of a kinetic theory of gas. The molecules do not interact with each other. The gas molecules is not interaction with each other. The collision of gas molecules with themselves or all will be elastic. The momentum is a constant. Air kinetic energy. So these are the assumptions of the kinetic theory of gas. Now, derivation of a kinetic theory of gas. So consider one cubic box contains a gas. Consider a cubic box of length L filled with a gas molecule of mass m, moving along x-axis with velocity dx. Therefore, its momentum is mvx. The gas molecules collides with the wall. At wall 1, it collides at n momentums is mvx. Similarly, the molecules collide wall 2. reversing the momentum minus the x. Thus, the change in momentum is given by change in momentum P is equal to mvx minus bracket minus mvx. So minus minus get the plus. So we get the 2 mvx. That is the equation number. After the collision, the molecule travels a distance of 2L before colliding again with wall. Thus, the time taken is given. Time is equal to distance traveled. So distance traveled is the 2L. We have the consider length L. So one wall is the L, second wall is the second. So we consider as a 2L. Upon Bx, this continuous collision carry a force is given. Force is equal to change in momentum upon. So you have to write change in P or change in T. Now we have to put the values in equation 1 and 2. So force is equal to 2 mvx upon 2L upon x. So force is equal to mv square x upon x equation. The continuous collision also exert pressure on the wall is given by pressure is equal to force upon A. F upon pressure is equal to mv square x upon L upon L square. So it makes it P is equal to mv square x L raised to 1 and L raised to 2. It becomes a L raised to 2. So it becomes a equation. We know that the gas is made up of n number of molecules move in all possible directions. Thus, the pressure exerted on wall 1 by the collision of number of gas molecules is given by P is equal to n number of molecules. So here in equation get the capital N and mv square x upon the average velocity or velocity component of all gas molecules colliding with wall along x direction v is equal to, so replace the value of L Q by. So P is equal to n mv square x upon. Now here three coordinates of Q, Px, Py and Pz, that is the independent speed of p direction of gas molecule. If we consider the gas molecule involved, then v square x is equal to v square y is equal to v square z. Hence, v square is equal to 3 v square x, or v square x is equal to 1 by 3 v square. So, substituting that above value in equation 6, you will get P is equal to n mv square 3, or PV is equal to 1 by 3 n mv square. So this equation above is known as kinetic theory of gas. The velocity in the kinetic gas equation is known as root mean square velocity and is given by the equation VRMS. V1 square, V2 square, V3 square up to V raised to n square. It is the square upon n. So we use this equation to calculate RMS velocity of gas, that is the root mean square velocity of gas molecules at any given temperature and pressure. So that is the equation of a kinetic theory of gas. Now next concept is the kinetic theory of gas law. There is the number of gas law starting with an ideal gas. So from the kinetic theory of gas equation, you have to know PV is equal to 1 by 3 nmv square. The problem with equation that the RMS velocity is not convenient quantity to make. We will replace it with a more convenient quantity, temperature, which can easily measure by a thermometer. The kinetic energy equation from classical mechanics is half of the mass times square of velocity. So Ek is equal to 1 upon 2 mv. So that is the kinetic energy equation of classical mechanics. So it also from a statistical mechanics, kinetic energy of for monotonic gas is given as Ek is equal to 3 by 2 about into K. So that is the equation number 3. So here K is Boltzmann constant is 1.380 into 10 raised to minus 23 joules per. From equation 1 and 2, Ek is equal to 1 half mv square is equal to 3 by 2 K. So both sides same term are cancelled, that is the 1 by 2. So you will get the mv square from left hand side and 3 kt from right hand side. So put this equation in above value. PV is equal to 1 by 3 and 3 kt. So 3 are cancelled. So you will get the PV at kt. So K is the Boltzmann constant, is also ratio of the gas constant to the Avogadros constant. Any. Put that value in above equation. K is equal to R upon. So PV is equal to nRT upon A. So here nRT V terms shift by that right side, that is the V upon Na. So in the above equation, ratio of the mole of gas is equal to N, small n is equal to N upon N. So P is equal to small nRT upon T. So we again shifted to the left side. PV is equal to nR. So that is the ideal gas equation. PV is equal to nR. Is derived using a kinetic theory of gas equation. Now second gas law, that is the Boyle's law. From the kinetic theory of gas equation is PV is equal to 1 by 3 mv square. That is the equation number. So since V square directly proportional to the temperature, if the temperature of gas kept constant for given mass of a gas constant, that is the M constant. So PV is equal to constant. So here mass is constant, velocity is constant, and number of gas. So that is P is directly proportional to the 1 upon. So it means that pressure of given mass of gas is inversely proportional to its volume at constant temperature, which is a Boyle's. Now third law is the Charles law. From the kinetic theory of gas equation is PV is equal to 1 upon 3 n mv square. That is the equation number 1. We have to write V is equal to 1 upon 3p n mv square. That is the equation number 2. Since V square directly proportional to the T, if the pressure of gas kept in constant for a given mass of gas. So here volume of given mass of gas is directly proportional to its at absolute temperature at constant pressure, which is a charge. Now next law is a Dalton's law. From a kinetic theory of gas equation, PV is equal to 1 by 3 n mv square. That is the equation number 1. Consider a mixture of gas, then P1, P2, Pn are the partial pressures of the respective gases. Then from the kinetic theory of gases, we have P1 is equal to 1 upon PV N1 square, N1, M1, P1 square. So same as P2, 1 by 3 V N2, M2, P2 square. Up to 1 by 3 Nn, Mn, Pn. According to Dalton's law, the total pressure exerted by mixture of pressure is equal to the sum of the pressure exerted by each gas. So total pressure is equal to P1 plus P2 up to P. So that is the equation number 2. So put up the value 1 by 3 V and N1 M1 V1 square up to 1 by 3 V and then Mn Vs. So you have to get the combined terms, that is the outside, that is the Pt is equal to 1 by 3 N1 M1 V1 square up to Nn Mn Vs. So that the different terms are in a bracket. Since V square is directly proportional to the temperature, if the temperature of mixture of gas kept same, so their kinetic energy per gas molecule must be. Now next gas law of kinetic theory of gas law, that is the Avogadros law. From the kinetic theory of gas equation is PV is equal to 1 by 3 NmV square. That is the equation number 1. Consider a mixture of gas, then P1, P2 up to Pn are the partial pressure of the respective gases. Then from the kinetic theory of gases, we have P1 is equal to 1 by 3 N1 M1 V1 square up to Pn 1 by 3 Nn Mn Vn square. Avogadros law is statement that under the same condition of temperature or pressure, equal volume of a different gases contain an equal number of molecules. These empirical relation can be derived from the kinetic theory of gases under the assumption of perfect ideal gas. The law is approximately valid for real gases at the sufficiently low pressure and high temperature if pressure and number of molecules are proportional for a given temperature and volume, that is the P1 upon N1 is equal to P2 upon up to Pn upon Nn. The specific number of molecules in 1 gram mole of substance is defined as the molecular weight in gram is 6.02214076 into 10 raised to 23 or 10 raised to 26. A quantity is known as Avogadros number or the Avogadros mass. Now, next gas law of kinetic theory of gas law is a Graham's. In the 19th century, Graham studied the rate of infusion of gases through very small holes in porous membranes. He observed the rate of effusion to be inversely proportional to the square root of the density of the gas, provided that the pressure and temperature were held constant. Since the density of gas is proportional to its molecular weight, Graham's law can be stated as effusion rate A upon effusion rate B is equal to m of P upon m of E. That is the square root term. It is the pressure and temperature is the constant. So what is the square root? Density of gas. Graham's law describes how helium-filled balloon loses its gas more quickly than air-filled balloon.